Life is too short to work at a crappy company. That's why Software Engineering Daily is proud to be sponsored by Hired.com, the job marketplace for software engineers. If you accept a job through Hired, they will give you a $2,000 bonus. But as an extra bonus to our listeners, you can get an additional $2,000. That's $4,000 total if you sign up by going to softwareengineeringdaily.com and using the link on the right side of the page to sign up. Hired.com will set you up with 5 great companies for interviews. These are companies like Stripe, Facebook, Uber, companies you would actually want to work for, where you can go and learn the cutting edge of software engineering. Go to softwareengineeringdaily.com, click on the banner on the right, and try out Hired.com. Spotify is a streaming music service that uses data science extensively to recommend music to customers, generate playlists, and build lots of other aspects of the product. Boxun Zhang is a data scientist at Spotify. Boxun, welcome to Software Engineering Daily.
My pleasure.
So prior to your work as a data scientist at Spotify, you did a PhD in parallel and distributed systems. What is the overlap between distributed systems and data science?
Well, I think this really depends because within distributed system study, there are many different fields people focus. So if your research focus is on, let's say, measuring system dynamics or modeling system behavior or user behavior in large-scale distributed systems, I would say it's quite similar to most of the data science work carried on in companies. It's very, the procedure is very very much like you set up some measurement, infrastructure. You start collecting data, then you have the data, you clean the data, you look at the data, you generate some insights, and in the end, the insights either end up in a academic publication or ended up in a company report. I think in that sense, the overlap is quite big. The gap is very small if you want to jump from your PhD in that part into data science work. But on the other hand, if your focus is more on algorithm and protocol design for distributed system, for example, you want to say, I want to develop a super strong fault tolerance algorithm for data storage for large-scale distributed systems, then I would say your focus is more on the more computer science side, not much on the data science side. So in that case, the gap is there.
Interesting. So I feel like data science is somewhat of a newer term. And in the past, there were certainly data analytics and stuff that people would do just, using a database. But, maybe the term data science started coming around as the term distributed systems also started being widely important. Do you think is there some kind of chronological overlap between when data science started becoming prominent and when distributed systems started being really important?
So I think this is a very interesting question. So the way I see it is, so when I think these two parts really started when the term big data gets started. So at a certain point when people realize they have too much data to store for single machines. And then people start thinking about, okay, we should have Hadoop, we should have HDFS, all kinds of distributed storage system. And I think that's also the time people realize using the traditional tools or techniques to analyze data becomes more and more challenging. And that's the time when people start looking into more advanced techniques or models or tools to analyze the data. I think that's more like the way I see why data science came to the scene, after data analytics. So there's certainly a sort of overlap between these two.
Yeah. So let's talk about Spotify. From a high level, what is Spotify's approach to machine learning and data science?
So I think Spotify now is quite big. It's not really like a small startup anymore. So we have lots of teams working on very different projects over the company. And apparently different teams have different approaches. But from what I know, Spotify is many Spotify teams take a very applied approach when it comes to machine learning or data science, which means we spend lots of time researching the problems we have, and then we apply existing techniques, either from machine learning or data science, to our problems. Then, we get our result. So, but on the other hand, we also have, teams building our recommender systems who spend lots of time researching new models or new method that suit our need. So I would say it's more like a hybrid approach.
Okay, interesting. I saw a slide share from Spotify that explored the evolution of big data at Spotify. That's what it's called, the evolution of big data at Spotify. I'll put it in the show notes. I'd like to go through some of that history, and hopefully as we go along, we can tie in how this big data architecture feeds into the practice of data science at Spotify. But I guess from your point of view, how has Spotify's big data architecture evolved over time?
So this could be a fairly long story, but I will cut it short. So when I joined Spotify, that was at the beginning of 2013. So back then we had around 200 nodes, maybe slightly more than 200 nodes in our Hadoop cluster. And nowadays, if you look at the cluster, I think we have more than 1,500 nodes, and it's still growing. So the scale of the cluster is totally different nowadays. And during this 2 years, there are lots of things happened. So the first we switched from a system called Log Archiver to Kafka for more efficient and reliable log delivery to HDFS. And we switched away from Hadoop streaming using Python to Crunch for more efficient data processing. And also during this time, we built a lot of tools around Hadoop. So, for our internal users, so we can easily use the cluster. So, for example, one tool we built is a sort of data retention platform. Previously, without this tool, you can easily delete 1 terabyte of data, by one bash command line. But now with this retention tool, we can actually, save the data in a sort of, trash can for each user. So if you mistakenly delete the data, you can actually get it back. So we have built lots of those small tools that makes the whole experience getting better and better over time.
Great. Yeah, we can go through some of those points individually. But as a data scientist, do you need to understand this big data architecture well, or do you just need to understand how you consume the outputs of this architecture?
I would say this depends on your background, as a data scientist. So for me, my background is purely in computer science. So for me, it's quite straightforward to understand the underlying technology stack. But I can also imagine for data scientists who come from different backgrounds, for example, physics or chemistry, there might be a gap to understand the underlying, technology. And also for many cases, I wouldn't really say it's necessary to understand the underlying technology, because in the end, data scientists really focus on the data. So to put it in a more extreme context, I wouldn't really say once I have the data, I don't really care where the data come from, to be honest. As long as I can make sure the data is correct, is reliable, I can, as long as I understand what's going on, it's fine.
We did a show recently about data engineering. There's like this kind of new term called the data engineer that, in some companies, the data engineer will be, will kind of do this stuff like data cleaning and setting up these data pipelines and really try to relieve the operational burden from the data scientist, so that the data scientist can really think more about statistics and how to build machine learning models, I guess. And but do you see this as a dichotomy, or does this separation of roles exist at Spotify, or do the data scientists like yourself, do you also do a fair amount of data engineering?
It certainly exists in Spotify, because when the company or when your data grows to a certain scale, I think these two aspects of, let's say data science work, becomes very much separable, and it requires very different skill set. So in Spotify, I would say data engineers have a much stronger emphasis on the computer science skills, the skills for building reliable backend systems. And also, of course, they should also have more like data-driven mentality. So, for example, people should be more sensitive to errors in data. For example, if they should have a sense of data quality. About all outliers. Some weird numbers going on when they build the pipeline. They should have a sense of that. But that's not really their main focus. Their focus is really on the infrastructure to make the infrastructure more reliable, more accessible to data scientists. And on the other hand, data scientists are, as you said, data scientists really focus on the more statistical skills, machine learning skills, and modeling skills. So we do have this separation.
What kinds of data is Spotify using? What kinds of data do you have to accumulate, and like at what volume?
So for Spotify, we collect data from our client, so we can understand, how users use the product, so we can improve the product in the future. So if you look at our Hadoop ecosystem, basically, our HDFS storage, so we have more than 40 petabyte of data. So every day we have about 30 terabyte of data ingested from Kafka, and our own pipelines also generate another 400 terabyte of data within our Hadoop cluster. If you look outside the Hadoop cluster, count all the servers we have, and also the raw audio files we have, for our service, we probably have more than 200 petabyte of data, and is growing pretty fast as well.
Okay. And I've heard that data scientists often spend up to 80% of their time cleaning data. As you said, certainly at a mature organization like Spotify, maybe you've broken up the role of data cleaning into a separate type of employee. But also you could just have tools and processes in place, or just be collecting the data in a well-formed fashion that reduces the amount of time spent cleaning data. So I'm just curious about the data collection process and how that has become, well, just from an organizational standpoint, how do you organize the data? How do you reduce the amount of time that you would otherwise spend cleaning that data?
So I think the way we do it is to set up dedicated teams responsible for the process of data ingestion and data cleaning, or building the core data sets that are used by other data scientists or other teams. So by aggregating the responsibility of, cleaning the data, the amount of time, needed from other teams or other data scientists to clean the data is reduced dramatically. But in reality, that's not all the case, because the knowledge each team has about how they should clean the data is often limited. And also, as we discover more and more insights from our data, we will learn more details about, learn, let's say, more knowledge about how should we clean data. We will identify more, let's say, outliers in various use cases. So I would say in Spotify, there are few teams, responsible for cleaning the data for the whole company, building the core data set. And when data scientists or other teams start using those data sets, we will do another round of data cleaning. But those cleaning are more for specific use cases.
As you said, there was a period of time where Spotify had an architecture called Log Archiver that interfaced with Hadoop. Can you tell me more about Log Archiver?
Certainly. So Log Archiver was a system we used to deliver our logging data from our servers, like we call it access point, to our HDFS storage. So that's the system we built a long time ago, and it was built around rsync and SCP, and we cron those jobs, so it runs regularly to transfer data from our servers to our data center. So it was a very simple tool overall.
And why did it fail on a regular basis?
So, as you can tell, if we have scripts, using rsync and SCP, and it was croned, so it's not such a big surprise to see it fails every now and then, because you basically have very little control, very little monitoring going on there. And that's not the only reason why we replaced it later with the Kafka. Another reason is the performance for delivering the log was really poor. So the time needed for the data to be transferred from the server to HDFS was around a few hours. That was a very long time, especially compared to the performance we gained by using Kafka.
So speaking of Kafka, Kafka now is used by Spotify to accomplish what Log Archiver used to accomplish. What were the benefits of starting to use Kafka?
So I would say there are a few big benefits. So the first one is performance. Either from both the throughput point of view and also from the time we need to transfer the data. So throughput-wise, Kafka is great. We can transfer lots of data in very short time without any problem. And also the amount of time needed to transfer the data to our storage, to HDFS, is reduced from hours, the time we used, when we use Log Archiver, to seconds. So I would say that's a significant improvement over performance. Another benefit is scalability. So we don't have to cron the Kafka jobs like what we did for Log Archiver, and it's designed to scale to large systems. So I would say those are the two major benefits we gain by using Kafka.
Are there any unique use cases for how you are using Kafka at Spotify that the listeners might find interesting?
So I would say one interesting point is Spotify doesn't really use the vanilla version of Kafka. We actually build lots of custom parts or components around Kafka for our use case. So back then we started using Kafka 0.7. I think that was the time Kafka doesn't support like replication or more, doesn't have the reliability guarantee. So we actually build custom components for reliable end-to-end delivery by enabling replication of the messages. And also we build our own components for encryption and compression for our data. So together with Kafka and our customized components, we actually, it suits our use case.
Okay, got it. Spotify also created a tool called Luigi. What is Luigi?
So Luigi is a tool for building complex data pipeline or any pipeline in general. So Luigi is very similar to other build automation tools like Make and End. So what's the scenario we are targeting is, so let's say you want to build a machine learning model, and to build a model, you have to fetch data from multiple data sources. For example, you can get data from a Postgres database, and then you want to use some data from Hadoop cluster, and then you want to combine these two data sources together and feed the data into the machine learning pipeline. And then you want to output the result into another Postgres database. And Luigi is a framework that facilitates this process. Luigi helps us to chain all those pipelines together in a very easy way. So we don't have to do it manually. And it handles all the dependencies really well.
When you chose to build Luigi, were there any open source alternatives already existing that you could have considered?
I'm not quite sure. Probably there are some, but but my guess is, Luigi Luigi was built a long time ago, and I guess even though there were some alternative out there. Probably none of them or very few of them fit Spotify's use case. Because back then, Spotify was using Hadoop streaming drastically, and also we have our own unique use case. So I believe the reason why we built Luigi is we didn't find any alternative that fit into our own use case.
So what are the problems that the big problems that you encountered with Hadoop in the past and in the present, and what are the persistent themes in the Hadoop problems that you encounter at Spotify?
So in the past, I think uptime was a big problem. That was more like before 2013. So the uptime of our Hadoop cluster, the small cluster we had, was not so great. So that basically make the cluster not that usable if you see, okay, the cluster is down very often. And now the cluster is very stable, it runs very smoothly. So then, the problem we have, I wouldn't really call it a problem, because we have a fast-growing need for data and insights. So there are so many pipelines running. So we always run into this contention problem. We are sort of competing within Spotify for the Hadoop cluster to run our own data pipelines.
Got it. So let's zoom out a bit and talk about the end user experience, the end user benefits from the big data tools that you have in place. From an end user point of view, how did the experience improve due to the improvements in big data architecture from tools like Kafka and Luigi? I know that's sort of an indirect long-term improvement that would result, but what did improve over time?
So I would say by having more advanced tools in our big data ecosystem, I think the biggest improvement is the feedback loop, or the time we need to build a core data set that supports user-facing features. And also, since the time we need to build those data sets is reduced drastically over time, we have more time to actually do more quality control of the data set to make sure everything is correct. So overall, I think that's already a big gain for the company, because with those tools in place, it's pretty easy and feasible to support lots of user-facing features using our data.
Now that we've talked about Spotify's architecture in an abstract sense, in the big data architectural sense, let's talk about the type of work that such an architecture supports, like the type of data science that you're doing. What do you work on at Spotify? What is the type of data science work that you're doing day to day? So in the past, I've done all kinds of work, under the data science term, quite a bit. But nowadays, I spend most of my time doing long-term projects. And recently, I spent most of my time studying user sessions and its properties, basically how users use our app in general. Tell me about your workflow. Like, what would be a problem that you would solve, and how would you approach it, and what technologies would you use? So
I would say I don't really have a very fixed workflow, but one thing is I'm pretty sure is I always start with a problem, and I always start to define a problem. So after I have the problem, I start collecting some data, from Hadoop or HDFS or some database, and then I will look at the data, clean the data a little bit, do some exploratory statistic analysis. And after that, I spent fairly amount of time reading academic papers. And basically, I try to get to know what have been done by other companies or by other universities in the past. And then I come up with my own solution. And after that, I build simple prototype. If the prototype works well, I talk to engineering team, so to see if we want to build a proper system around it. So regarding the technologies, I would say I use pretty standard tools. So to get the data, to prepare the data, I use Hadoop, and to analyze the data or to build models, I use Python and R. I find IPython notebook or Jupyter notebook nowadays is particularly useful for sharing and reviewing others' work. One last point is recently I started using XGBoost, a very popular tool, machine learning library among Kaggle users. And that's a library for building boosted trees or gradient boosting models. And the performance is really superb. And I would really recommend, the audience to check it out.
Could you talk about that tool in more detail? Like, how does it? Give an example for how you might use that tool. It doesn't have to be a Spotify related example. I don't know. Maybe if you were studying oil data or something.
Sure. So XGBoost is a library, or it's more like a general purpose implementation for gradient boosting models.
And what is gradient boosting?
Gradient boosting model is more like a tree ensemble, similar to random forest. But the difference is, unlike random forest, the model will build lots of decision trees at the same time. But gradient boosting models will build one tree at each time. And each tree is built upon the data that that the previous model didn't perform well. So it's more like a process of self-correcting. So after proper tuning, in lots of practical use cases, I find out boosting models outperform random forest in many cases. So that's why in Spotify I started using boosted trees model. And this XGBoost library actually offers lots of interfaces to all other major languages used by data scientists, like Python, R, Julia. So it's extremely easy to use.
So there are probably some listeners who are confused by some of these machine learning terms. Could you define what a random forest is?
Sure. So random forest, as the name suggests, is basically a bunch of decision trees. So, and the way random forest is built is each decision tree in the forest is trained by a random sample of training data and randomly selected features. So in this way, random forest performs really well when there are lots of noise in the data. So the model is really robust because of this twofold randomization.
When you say random features, how are those features approached, or like what? Maybe you could define the term feature in the scope of a random forest.
So the feature is like feature in all other machine learning models. Basically, it's just like a numerical representation of your data. It's basically one value or one column in your a training sample. And the randomization here in random forest basically is about, for example, if your training set has 10 different features, 10 different columns, and random forest will take a random subset of these 10 columns to train a decision tree. So let's say one decision tree can be trained by the first 5 columns, and the other decision tree can be trained by another random 4 or 6 columns in your training set.
And in a given tree, is the goal to minimize or maximize this column, or does the user define that, or how does that work?
So the goal of each tree is the same as the goal for the random forest. For example, the goal of a machine learning task would be, I want to predict if a user will stream a song. And each tree will have the same goal, but using different training set, to train.
Okay, I understand. So when you're looking across these different trees, you're looking for like consistent patterns in how the different data sets that the different trees have correlated?
So imagine if you have, let's say, 1,000 trees trying to predict if a object is a cat, let's say. So when you have all the trees trained, it becomes a voting problem. So for example, you can have 800 out of 1,000 trees say, okay, that object is indeed a cat. And the other 200 trees might say, okay, that object is not a cat. So in the end, you will do a majority vote. You will take, you will basically conclude, okay, that object is a cat because, 800 out of 1,000 trees say so. In that case, the model will be much, much more reliable and accurate compared to one single decision tree, because one single decision tree is very vulnerable to noise in the data.
So this process of looking across the different trees and doing a majority vote, that's ensembling?
Yeah.
Okay. And is there a way to do ensembling where you're not looking for a binary outcome? Like what if you have a gradient of potential outcomes? Can you still do ensembling that way?
Yes, that's totally possible, because random forest can be used for both classification and regression problem, and the same for boosting models, gradient boosting models as well.
Okay, cool. Over Thanksgiving, I had a great idea for a web app. So instead of spending time with my family, I locked myself in a room and I started building this application using Express.js because I love full stack JavaScript. So I was testing my application locally and I was making great progress. So I decided to deploy it and share it with some of my friends and get some feedback. I used DigitalOcean. I signed up for an account using promo code SEDaily, and in 15 minutes, I had my app deployed to a server and running. It was that simple. This was really the first time I had used DigitalOcean. So if you're like me and you like building stuff and you have ideas for projects, give DigitalOcean a shot. It is the fastest and simplest way to deploy an application that I've ever used. If you want to give it a try, go to DigitalOcean.com and use the promo code SEDaily to get $10 in free credits. Check it out. So I'd like to define some other data science terms, some statistical terms while we're on this topic. What is K-means clustering?
Well, K-means clustering is probably, arguably the most popular clustering algorithm used out there. So it's extremely simple. So assuming you have 100 observations and you say I run a K-mean clustering algorithm to cluster those 100 observations into 5 clusters. So the algorithm will basically assign those observations into those 5 clusters with the goal of minimizing the within cluster distance of each observation to the mean in the cluster. So it might not be so clear from my description, but if you think about it, each cluster will have a centroid, so the central point of the cluster. And by assigning different observation into different clusters, you will be able to calculate this distance between each observation to the center of the cluster. And the goal of the algorithm is to find out the way or the centroid that can minimize the distance, the sum of the distance of all the observations within each cluster to the centroid. So basically, if the algorithm is successfully run, you will have clusters that have observations very close to each other.
Another term that we often hear when we're talking about machine learning and data science is gradient descent or statistical gradient descent. What is this and why is it so important to machine learning and data science?
So gradient descent is an algorithm that can find the local minimum of a function. So why, basically the way it works is, so when you have a function, with a few parameters, sometimes you want to say, I want to find the local minimum, and the gradient descent actually, do this by going to the negative direction of the derivative of the function. Basically, it's the gradient of the function. So it's more like if you visualize this, a two-dimensional place, a space with the two parameters, and and also the value of the function is more like a contour plot. It's more like you're walking down to the of the mountain, by applying gradient descent. And why it's important for machine learning is because if you look at linear regression, probably one of the most important machine learning algorithms out there. So the goal of linear regression is about minimizing the sum of squared residues between the predictions and the training data. And that can be achieved by applying gradient descent, because the sum of squared residues, or the objective function of linear regression, can be expressed as the parameters of the model. So by applying gradient descent, we can actually find out those parameters very easily.
Got it. So we did a show with a company called YHat, which builds tools that allow data scientists to collaborate more easily with software engineers. And it's interesting because you were talking about your work, and it sounds like you start off your work on a problem sort of siloed. You focus on this problem, you read the literature associated with it, you build some prototypes, and then you think about, is this a scalable solution? Should I give this? Should I either engineer this myself or hand it off to the software engineers? I'm curious about how the collaborative process between data scientists and engineers works at Spotify. Specifically, like once you've moved beyond this prototyping phase, how do you go to the phase of let's integrate this with the engineering teams in a scalable fashion?
I think this is a great question. I think lots of companies, are facing this problem now. So I would say, the way I sort of discovered the problem to work on is not really by, doing literature study or looking at the data by myself. So the way I'm doing it, and also is the way I find it very efficient, is I normally try to sit together or very close to a product team or engineering team. And by doing so, I get very close to the source of all kinds of challenging problems. So in that way, I can make sure all the problems I get are important problems to at least some teams in the company. So I will not have this crazy idea no one will benefit from even if I can solve them. So I think that's a very important lesson I learned in the past when I work in Spotify. So first, sit closer, with engineers and product teams. So you find, important problems to work on. And so let's say we find a problem and build a prototype. And the problem now is, how can we put it in production system? So there are multiple options for doing that. One obvious one is you hand over the code. There will be, let's say, proper engineers, refactor your code and re-implement everything. But another approach I took is I try to make my own machine learning pipeline or the machine learning code as good as possible. So it gets to a state that's almost ready to be integrated into a bigger pipeline. And even if the bigger pipeline is implemented in a different language, we have different ways to chain them together. For example, there might be some APIs, bridging different languages, for example, from Python to Java or from Python to C. Or we can simply store the output of the machine learning pipeline into a commonly accessible storage place like a database or HDFS, where another pipeline in the bigger system can pick it up later.
So are you saying that like sometimes the prototype or whatever code you write ends up being like just good enough for production? You just kind of have to plug it in and connect it to the right data store that other people are accessing?
So I wouldn't really say it's always the case, because after doing the data science work for some time, I wouldn't really say I'm still writing, let's say, production level code. But I mean, when I write, let's say, machine learning pipelines, I try to make it as good as possible according to the best practice in software engineering to make sure it's maintainable, let's say, extendable in the way. But still, I would say when we plug my, let's say, machine learning pipeline or code into a bigger system, there are lots of things we need to maybe reconsider because there might be other use cases we want to tackle, as a bigger system. So there will be changes to the code.
Yeah. So one interesting thing you said, about sitting with the people that are encountering those problems that you might end up wanting to tackle from a data science perspective. It reminds me of when I used to work at this trading company, and they would sit the engineers somewhat close to the traders because the traders are constantly encountering these certain problems, and the engineers are building products for the traders. So it really makes a lot of sense to have them kind of co-located with one another. So I think this is interesting. When you're building products for other people in the company, it makes sense to sit close to your users.
Yes, I think the key benefit of doing this kind of embedding or sitting together, or whatever we call it, is we can shorten the feedback loop between different teams drastically. And sometimes it's very, very critical. So, for example, in Spotify, between engineering teams or product teams to data scientists or analysts, sometimes if you don't sit together, people send emails across different teams, and there's no guarantee how fast you can get feedback for anything. Sometimes it happens fairly, fast. Sometimes it can take some time. But when you sit together with each other, you don't even need to send emails or talking through some messaging services. You can just talk to the guy next to you. You can just have a small chat, and you can just resolve the problem. So I find it extremely valuable and encouraging, actually, because you can literally see small progresses are made, and that's a very nice feeling.
Totally. So we've done several shows recently on these different streaming systems. This is kind of zooming out to a bigger picture, but there's all these streaming systems. There's like Storm, Spark Streaming, Samza, Flink, all these different things. I'm curious what your perspective is on why there are so many of these, and where we're going with all these different streaming systems. And maybe you could touch on how streaming systems are used at Spotify.
Sure. So first of all, I want to say I'm not an expert on the streaming system side, but my view on the fact we have so many new streaming systems coming out all the time these days is, I would say this is a sign of a new booming field or a very new requirement or demand from the industry. So previously, people were using Hadoop or other technologies for batch processing for quite a long time, I think in the past couple of years. And now people start realizing, okay, we have the data coming in all the time, and we don't want to wait for a couple of hours until our data is ready. So streaming becomes a very natural next step, I would say. But at the same time, I think from the industry, there's very diversified demand for using streaming system. People have very different use cases. And I would say none of the current streaming system is actually mature enough or big enough to cover all the use cases. That's why I think we are seeing so many new streaming systems, coming out and competing with each other. And personally, I think this is a very nice thing to have, and I think is very promising for the near future. Maybe in 1 or 2 years, we will have 1 or 2 very mature streaming system in place. Many companies will use. So regarding Spotify, I think we use streaming system for a couple of use cases. I think we have we use streaming system for ads targeting, and we use streaming system for personalization, and some other use cases. But it's not a huge use case in Spotify at this moment.
Is that because the sensitivity of the of data processing is not super high? Like, I mean, I can imagine if a user listens to a song and then you need to run a machine learning algorithm on that user listening to a song, it's not a huge deal if the user's playlist gets updated in 24 hours or in 12 hours or whatever, rather than immediate.
I would say it depends. So, for example, if you look at our new feature, Discover Weekly, that feature is designed to give you new songs in the playlist every week. So in that case, using some batch processing, pipelines is not a problem at all. But on the other hand, think about another use case. For example, we want to personalize our recommendation based on your recent search queries. So in that case, having a few hours gap between the user actions and having the data in our system is not really acceptable, I would say, to build such features. So in the future, if we plan to do more real-time recommendation or real-time features, streaming system will become a must-have component.
Makes sense. So there was recently a product that was open sourced out of Google called TensorFlow. I don't know if you've looked at this much, but I'm curious if you have, what you think of TensorFlow.
So I would say, I would say everyone is looking or talking about TensorFlow now. It's a big thing from Google, certainly. So I haven't really spent too much time looking into the product, but from what I know, I can only say it's certainly very promising from the white paper I got from the website of TensorFlow. But I do need more time to try it out to see its real efficacy, for real data. Because TensorFlow itself is such a big product and it has so many components. I think most of the people need a lot more time to actually understand what it can do, what it cannot.
Yeah, I spoke to Greg Corrado yesterday, who is one of the guys who works on TensorFlow, and he was telling me about how, I didn't really understand this before I was interviewing him, but he was like, you can deploy machine learning models to people's phones, basically, and then have those models dynamically update with new information. And maybe this is something that is not a huge new deal, but I think of something like Spotify, where if you already if you had this pre-baked model deployed to your phone and it could update all on the client, all on the phone, then every time I listen to a new song, the machine learning can happen on the phone. I don't know. Maybe this is not a new thing. Maybe this is something that is already happening, and that's not the big breakthrough of TensorFlow. But
I mean, regardless of TensorFlow, but I think I would say the capability of deploying a model into user's device, I think, is hugely valuable. Because if you think about the traditional way of building recommender system, which is about getting all the users, let's say, listening, history, what songs users listen, and build this huge matrix, and doing matrix factorization and building lots of ensemble models in our server farms. That takes a lot of time and use lots of data. But if we can have smaller models, personalized to user level, we deploy them on each user's device, we can actually train those models or tweak those models only based on users' own data. So in that case, the amount of time and energy needed to train those models is so much smaller or lesser than actually training a huge model for all the users, all the content we have. So I would say that thing itself is hugely valuable. And I think Google had the machine learning model in Google Photos or some other Google product deployed on Android phones already.
Yeah. So it sounds like you're talking about the movement, like a movement from doing machine learning that is focused on things like collaborative filtering, where you need the entire user set, versus just having something that is much more individual user specific.
Yes, certainly. I mean, if you think about features like Google Now, the personal assistant, I mean, it's certainly a use case. For example, the model only rely on individual users' data. Probably it doesn't really care too much about what other users are doing. As long as it takes care of the current user, it's fine.
Right. So let's zoom out even further. What is the future of data science? Like when you're working day to day and you encounter certain operational problems or certain like systemic problems, and you say, gosh, in the future, there's no way data science is going to have a problem X. Like, what are the problems that are going to get sorted out over time? How will data science change and become easier?
So I would say in the future, I don't really know if the future is far future or near future, but in the future, we will have lots of tools available for data scientists or anyone who works with the data that can, takes over all the routine works nowadays data scientists need to do. For example, running basic diagnose over the data. For example, once I have a very complex data set, I want to say, okay, how my data set look like. And, even though it sounds pretty simple, but it might take quite some time to do this, because you have to run proper analysis for each column or each variable in your data set. You have to do some anomaly detection. There are lots of routine works. I think those work will be taken over completely by automated tools. I think there are already some tools like automatic statistician out there and Skytree Infinity out there to do this kind of work. So I would say, give those tools a few years, maybe 3 to 5 years. Those tools will be powerful enough to take over, to handle most of the routine work for data scientists. And as a result, I think data scientists will be pushed into a place that people need to focus more on, let's say, feature engineering part. Basically you spend most of your time thinking about what kind of data you want to fit into those, super awesome tools. So those tools or those, platform can give you a nice result. And also people will focus more on interpreting the results, from those tools and convert those insights into, the insights with the business values.
Yeah. So maybe this is the interpretation side that you're talking about, but how do you think we're going to move some of the job of the data scientist beyond a place that requires coding?
I would say it's possible. I think that also depends on the type of data science work. So I think it's very hard to predict if that will happen, because nowadays with data science, with the big data, with machine learning, there are so many possibilities for the future, even for the coming year.
Yeah, definitely. So I guess I want to close off with just a question. I would not normally ask this at all, but since you work at Spotify, and I'm just like really curious, what music do you listen to these days? What are you listening to?
Well, I think recently I listen lots of music from 70s or 80s, and I would say that's probably because the movie The Martian. In the movie they really put in lots of nice music from 70s and 80s. So like Starman from David Bowie. I don't know how many times I've listened to that song repeatedly. And from there, I started listening to music from Bob Marley, Fleetwood Mac, Queen, Eagles, Roxette, the Bangles, all sorts of big stars in the 70s and 80s.
Do you have any? I'm a huge fan of Spotify. I use Spotify probably like 2 to 3 hours per day. I don't know. I feel like there are a lot of features in it that maybe I haven't explored. I certainly use Discover Weekly, but do you have any recommendations for products I should check out? Like, for example, okay, so when you want to listen to 70s music, are you like going to the radio feature, or how are you discovering 70s music you want to hear?
So normally I go to Browse, so our basically editorial playlist. And there you normally find out music from different era in the 70s, 80s, 90s. And we also have a good categorization of different music genres. So for me, normally that's the starting point. And for example, I jump into a, let's say, rock music in 80s playlist. And I start looking to each track and check the artist page. And then another feature I use is related artists. So that's a great place for expanding the view of the music horizon.
When you're consuming music on Spotify, do you find yourself thinking about what in machine learning, like what machine learning stuff has led to this song being generated to you, or do you feel like you don't have enough of a grip on how recommendations are made at Spotify that you can actually conclusively trace that?
I would say, from my own perspective, because I know how the machine learning models work. So when I listen to, for example, Discover Weekly, I can sort of, I can certainly sense, how the recommendations are made. And I think I also talk to some of my friends who use Discover Weekly often. And I think, as a user outside Spotify, I think people can also sense, how it's generated, because one common, let's say, feedback I got is people say, okay, feels like this playlist or Discover Weekly is sort of personalized for my taste, because there are lots of music people sort of recognize in terms of genres or the mood or the artist type.
Yeah, definitely. Well, Boxun Zhang, thanks so much for coming out to Software Engineering Daily. It's been super interesting talking to you about Spotify and data science and machine learning and all this stuff. I really appreciate it.
Thank you very much. It's also my pleasure to talk to you.